Let's finish our discussion, only about 5 minutes left probably, on the different types of non-Euclidean geometries. All right, and so by now you've watched the other two, or you watched one video and read and looked at pictures at another website. So you know that Euclidean geometry is done on a plane, right, a flat surface. We also have spherical geometry, which we looked at a little bit. We're not going to do anything to study this hyperbolic geometry, but we can do geometry on what's known as a hyperplane. All right, so something with negative curvature. This, the sphere has positive curvature, whereas this has negative curvature. And what you notice about a triangle on this is it has less than 180 degrees. Okay, over on the sphere, our triangle can have a maximum of 3 right angles, so it can have 270 degrees in it, or it will always, though, any triangle we draw on the sphere is going to have greater than 180 degrees. So here's just another visual for you. So like the hyperplane up above, it talked about a saddle, right? But any surface that has negative curvature, right, is considered the hyperbolic space. And then the rules for geometry are also different there. I want to bring you back to some memories that you probably have in high school geometry. Pretend those are parallel lines. It's really hard for me to draw good lines on here. So pretend these lines are parallel. And you spent a lot of time in high school talking about alternate interior angles, right? And how alternate interior angles are congruent. And I always refer to this as the Z rule, right? If you can form a Z with them, and we have this other pair of the ones I didn't fill in, I'll call them 3 and 4. If you can fit a either forward or backward Z, right, you have alternate interior angles. Because when we're working in Euclidean geometry on our flat plane, we can actually prove that a triangle has to have 180 degrees in it. And so why can we prove something over here and yet it's not true in non-Euclidean geometry? And when we go to prove that a triangle has 180 degrees in it, okay, so let's call this angle A, angle B, and angle C. All right, and pretend that we don't know that A plus B plus C equals 180. But we can agree, right? Let's all assume that we can agree that this pair of angles, which is known as a linear pair, right? These have to add up to 180 degrees. And I think we agree on that because we agreed that a complete rotation is 360 degrees, right? So therefore, halfway around has to be 180 degrees. So what we can do to prove that a triangle has 180 degrees, it depends entirely on the fact that I have parallel lines. All right, well, remember what happened in spherical geometry. There are no parallel lines. All right, so what's kind of cool about math and the way things build in math is when we're working through something in math, we have fact A, and that leads us to prove B. Then from B, we prove C. Then from C, we prove D, right? And then from D, we get E, F, G, H, I, J, K, right? And so that's how math builds. What happens though is like in non-Euclidean geometry, I don't have parallel lines. I don't have this thing called the parallel postulate. Therefore, I start off with this relationship and say, oh, wait a minute, I don't have C, right? If I don't have C, then I can't have D, and that means everything else has to change, right? So if I don't have C, then and B leads me to something different, let's call it like K. I do have B, but then it leads me to K, right? I don't get D, E, F, G, H, I, and so on. I would get like P, Q, R, S, T, U, V, right? Other facts. right? And so then I would get this whole new set of facts. So the fact that I don't have parallel lines in non-Euclidean geometry, in spherical geometry, really changes the relationships that you have always studied. All right, because again, to prove that a triangle has 180 degrees, there's my Z, which means that has to be angle A. And then I would have a Z going this way. Okay, which means this has to be B, right? So this angle here has to be A, this is already labeled C, and this has to be B. Therefore, because of alternate interior angles and parallel lines, that's how I know that A plus C plus B, I'm going to put it in that order, right? Has to be equal 180 degrees. Okay, but without parallel lines, I don't have that relationship anymore. So just a couple other interesting things to look at. I encourage you to do what I did the other day. If you have a tennis ball and a couple of thumbtacks, right? And take a look at how if you place something or at the with the orange, right? If you place that right at the, like the stem part right up at the top, and then you cut a quarter of that sphere, right? You will notice that these are all right angles, all right? And this talks about going down to the equator, right? And then going a quarter of the way around the world and creating this triangle with 3 right angles. Also, we've talked about flight paths. And so I hope you have learned that flights don't fly on a straight line because a straight line is not the closest distance between 2 points on a sphere. Okay, it is on a plane, but an arc measures the shortest distance on a sphere. So what happens is if we take these 2 cities, right, Florida and then this city in the Philippines, if I draw the great circle, okay, and I've got it over here, and it's sort of hard to tell, like here, this black line is showing what it would look like if I flew straight, which we feel like that looks like the shortest path, but it's not. And so what I do is I draw this great circle, and it probably doesn't look like I drew a great circle on here. It's sort of hard to tell when you're looking at something in 3 dimensions on a 2-dimensional surface. This circle would have to be centered. So like this line actually has to go like back in more, if that makes sense. The center of this has to be the center of the earth, right? The center of my sphere. So I did, it doesn't really look like it, but I did draw a great circle. All right. I show some pictures here of great circles where the center of that circle has to be the center of the universe. This is known as a minor circle, and this is not a great circle. Okay, so we would not use this to find the shortest distance between 2 points on a sphere, right? That something like this would not determine a flight path. Okay, it has to be a great circle. And so we learned why there's no parallel lines, right? All great circles intersect twice, right? So every set of great circles has 2 intersection points, therefore there's no parallel lines. All lines intersect twice. That's something different. So again, I hope, you know, one of our goals in this course is you tend to think that the things that you have learned about in high school are the limits to what there is in the world as far as math. And so I wanted to show you that there are some things that there's some questions that we never thought to ask before. All right. And there's different fields of studies related to mathematics that you never had the opportunity to even touch upon during high school. So thanks for watching, and we'll go ahead and call it a day.